Hi everyone, my name is Han Zhang. Today I want to talk about a hierarchical approach to multi-agent pathfinding. The multi-agent pathfinding problem, or MAPATH, is the problem of finding a set of collision-free paths for multiple agents given their start location and goal location. The MAPATH problem is closely related to many real-world applications, like automated warehouse or multi-drone delivery system. Solving MAPATH optimally is known to be NP-hard. If we place different categories of MAPATH algorithm in a 2D axis of solution cost versus runtime, optimal or bounded suboptimal MAPATH algorithm finds solution with lower cost. However, their runtime can dramatically increase with more agents and a larger map. At the meantime, greedy MAPATH algorithms are able to scale to large MAPATH instances, but their solution costs are often high. The idea behind this work is to decompose a MAPATH instance with a special hierarchy. We partition a map into multiple regions, and in each region, we can use MAPATH algorithm with good solution quality, while the total runtime is still affordable. In this paper, we propose a novel MAPATH algorithm called Hierarchical Multi-Agent Path Planner, or HMAP. Our experimental result shows that HMAP is scalable and yields solutions with lower costs on various maps. Although the idea of spatial hierarchy seems straightforward, there are only few existing work exploiting this idea. One of them is the Spatially Distributed Multi-Agent Planner, or SDP, which partitions a map into high contention and low contention regions. Different from HMAP, SDP does not partition the map if no high contention regions are found. And SDP can only solve MAPATH instances in which none of the start and goal locations are inside high contention region, which limit the application of SDP. Another one is Rusty MAPATH. Like HMAP, Rusty MAPATH partitions a map into several regions. Unlike HMAP, Rusty MAPATH has to synchronize the execution of the high-level paths or plans of all agents, causing agents unnecessarily wait for other agents, which impact the solution quality negatively. Here, we provide an overview of HMAP. Given a MAPATH instance, HMAP first partitions the map into multiple regions. Here, HMAP partitions the map into 4 regions, namely R1 to R4. Then, a high-level planner is responsible for finding a sequence of regions for each agent to visit. In the beginning, each regional planner finds a path for each of its agents to their next region. HMAP then finds the earliest time step where there is an agent reach the boundary to its next region, and the regional planner of that region needs to plan the entrance time step and the path for this agent. Once the entrance time steps are determined, the entrance location is determined as well, and they will no longer change. Each time a regional planner is invoked, it's allowed to modify the entire path inside the region of all its agents, as long as the entrance time step and entrance location are satisfied. In our example, at time step 2, agent 3 reached the boundary to its next region R2, and the regional planner in R2 needs to plan the entrance time step for agent 3. Once the entrance time step and location is determined, in the future iteration, when the regional planner in R2 or R4 replan the path, the entrance time step and entrance location of A3 should always be satisfied. HMAP repeats this process until the paths of all agents to their goals are found, and return this path as the solution. While the overview is simple, HMAP needs to deal with technical issues such as two adjacent regions send agents through the same edge from different directions at the same time, or delay of agents when they when they are exiting cause the original plan of other agents infeasible. Please refer to our paper for more detail on HMAP. In our experiment, we did not compare HMAP to SDP since we were not able to get a copy of their code. Here, we show the average makespan and number of moves of rusty makepath and HMAP on the 60 x 60 empty grid for different number of agents. Both algorithms were able to solve all instances within the given time limit. HMAP used the same partition as rusty makepath. You can see that the average makespan of the solution of HMAP was less than half of the average makespan of the ones of rusty makepath for instances with more than 576 agents, which is a significant advantage in terms of solution quality. In this experiment, we compare HMAP to these three algorithms. One is ECBS, which is a bounded suboptimal makepath algorithm, and the suboptimality factor is set to 1.2. CA star, which is a greedy makepath algorithm which plans one agent at a time, and WHCA star, which is a windowed version of CA star which plans only for a limited time window, one at a time. Here we show our experimental result in two different maps. One is a city map and the other is a warehouse map. For each algorithm, we show the success rate, which is the percentage of instances solved within the time limit, and is higher the better. We also show the average pass cost, which is the lower the better. You can see HMAP outperforms all three algorithms in terms of scalability as the number of agents increase. Compared to CA star and WHCA star, HMAP improved pass cost by more than 10% for large instances. To conclude this paper, we propose HMAP for solving the makepath problem with a special hierarchy. Our experimental result shows that HMAP is scalable and yields solutions with lower costs on various maps. Future work include HMAP with theoretical guarantee, automated map partitioning, and congestion-aware high-level planning. Thanks for listening.